So we're talking about the idea that in many cases we may not want to draw, when we're sketching, an accurate representation of what a response looks like, but rather a caricatured version of that response. And the benefits of a caricature are, in weird ways, they are actually more recognizable because we have exaggerated certain effects. If somebody has slightly big ears, you'll draw them like an elephant, right? And if they wear glasses, you'll draw the glasses super big. If they maybe have a big nose, you'll exaggerate that. If they have a small nose, you'll draw it like it's almost not there. So you're exaggerating these effects. Now, in a sketch of a process response, in the case of a first order response, I'm looking for some very specific things. These are the things that I've spent a lot of time talking about in class. I'm looking for you to explain or to show me that you understand that if this time is 0, then a first order response will start responding at time 0. And it will start responding in a first order discontinuous way, sharp corner, right? So because this is a first order system, right, I'm expecting these characteristics. For a step response, note, I'm expecting a sharp response at 0. I'm expecting you to show me that you understand what the time constant is, right? So that I expect you to show me in one of the following possible ways, either in the box way, right, where if I extend that initial response up, tangent to the initial response, I hit a box which is defined by k and tau. And remember, in this case, the number there is 10 and the number here is 5, right? And so I'm expecting you to either draw the box, or when you draw the sketch, now notice, I'm not taking a great deal of pain to make this be an exact step response. I'm pretty sure if you calculate the actual function and you overlay it on top of my function, it won't be exactly the same. But I'm trying to exaggerate these effects. And I'm zooming in on a part that allows me to see those effects, right? So I want to make it clear to the examiner for knowing these properties and being able to relate them. So maybe I give you something like a step response, but probably not. Probably I want you to understand that the same question can be asked for other kinds of inputs. And that you should be able to draw, now assuming if that's a gain of 5, if this is the input, if that's u, starting at 0 over there and going maybe to 1 over here, I expect every one of you to be able to know that that change, if that goes from 0 to 1, the output of that first order system will go from 0 to 5. How do I know that? Because the gain of the first order system is 5. The gain tells me the eventual output of the system when subjected to a step input, and there's a little bit of a bump in the road, but if you zoom out far enough, that thing does look like a step input. Everybody with me? And so I know I've got the same eventual behavior, that asymptotic behavior going to 5 as I had when I had a unit step input. Now, also, nothing will happen while the input is 0. And the output will only start changing once the input starts changing. However, in this case, the output will not have a sharp corner. The sharp corner is because of the discontinuity in the input. This input does not have a discontinuity. It is a continuous input. It is first order continuous, the input here, right? Which means that I expect the output to be second order continuous. Another way of thinking about this is that the ramp response of a first order process resembles the step response of a second order process. The ramp response of a first order process resembles the step response of a second order process. Why? Because the ramp is the integral of the step, and the output of a first order system and the output of a second order system is related through integration, right? So from first order to second order, I add an S below the line. So there's this kind of resemblance that I expect there. Now, I've been talking about this idea that integrating the input results in integration of the output a couple of times, and I think not everybody's following me. I'm going to finish up this example and then just walk you through that. It's mathematically obvious, but maybe it's useful if somebody just points it out to you. So let me just finish this quickly. Okay, so remember I said it's going to be first order continuous. Let me just switch to a different color. I'll make it a bit bigger. So here's the response, right? So I know it's going to kind of go up like this, and that's kind of the response that I expect to see. Kind of-ish like a second order response. Now, the exact nature of the time constant and so on is not that important, but given some context for time, assuming that that's a relatively, let's say a relatively short time, so let's imagine that was something like 1 second, given that this is a 10-second time constant. And remember, for that kind of first order process, we're expecting that little bump to move up to there in about the time constant. Does everybody see why I'm saying up to there? Because that's about what I judge to be 2/3 of the way. That's kind of where I'm coming from, right? So if that's the response of that system, I'm expecting that kind of time. Now again, you are telling me all of these things in words, right? So you're making note. You're saying, look at this. I know that this isn't just a step. This is not a step response. Locally, at that point, it is actually a ramp response. And because it's a ramp response, now you can easily go and memorize. The textbook does have like a ramp response that you could go and memorize. You can reason through this a couple of ways, but I need you to understand that if I draw a picture like this, you don't just draw the step response that you've memorized. You understand exactly how this response will actually look. So you're going to spend some time actually going through. There are plenty of test questions like this. There's a notebook that generates random system responses so that you can kind of train yourself and kind of guess what the response will look like, just knowing the poles and zeros or just knowing the transfer function. If you want to practice this skill, that's how I recommend that you do it. In general, I feel, well, you see, I struggle a lot with rote memorization, so I always underestimate your ability to memorize kind of what these questions look like. But this is what I mean by caricaturing. Right, so I'm expecting you to kind of highlight these responses. Now, what does that same thing look like for a second order response? I can do the same thing and say, well, now I've got a second order response. Let's make this really easy and make it like a very overdamped system. So let's say it's s squared plus 10s plus 1. How do I know that's a very overdamped system? Because s plus 1 squared is s squared plus 2s plus 1, right? And zeta is multiplied by that middle coefficient, and so that's a much bigger middle coefficient than I would have gotten by just multiplying two first orders in series. And so that's super overdamped, right? Now notice that I didn't do any math here. I mean, beyond like some very rudimentary mental multiplication, right? So I'm looking at that and I'm saying, okay, clearly that's super overdamped. It's also got a gain of 2. So what would be the same graph if this was a step response? What would that look like in my caricature world? Okay, so again, I'm like, well, I know that zeta is much bigger than 1, and so it's like overdamped. And so I'm expecting this kind of lazy response. And so that, if that's my first point, this is my first point over here. The overdamped behavior tells me that I'm going to have this lazy response. It's going to take a while before things happen. And I'm going to have no overshoot. And I'm going to again see this asymptotic result. But this time, I'm going to see, because it's super overdamped as well, I'm going to see the time constant much closer to the initial value than to the final value. Remember, even for just critically damped system, the time constant is, for critically damped system, the time constant is about a third of the way, or the time at which the response goes about a third of the way to its final value. Let's make that very clear. So if this is the initial value, that's the final value. The response is moving from the initial value to the final value. When it gets about a third of the way, that's about the time constant for critically damped systems. For overdamped systems, it gets even less, like the system is slower. Right? So again, I'm caricaturing here. If you were to plot this, I almost guarantee you that it's going to be a little bit sharper than I've drawn it. It's going to be a little bit faster. I've caricatured, I've accentuated this second order behavior so that it's recognizable, so that you don't miss it. Because sometimes when you just plot the response, it's like you can go, like if you really zoom in, you'll see there's a little flat piece there. But if you really zoomed out, it almost looks like a first order, for sometimes. And if you zoom out far enough, right, like you don't really see that. And I want to see it. I'm the examiner, right? I want to be sitting without my glasses, drinking a glass of wine, marking your papers. I don't want to be like, whoa, let me just get my glasses, let me just zoom in. Like as soon as I do that, there's like a little mark timer that starts clicking down, right? Like the more I'm looking for, I don't understand what's happening here. In semester tests, I'm like, oh, you know what, like you come and convince me that you know what's going on. I'll just mark you down. It's not my job to give you the benefit of the doubt. It's your job to show me that you know what's going on, right? So that's the caricature of critically and overdamped systems. What if this constant was much smaller? Now we know for that time constant of 1, how do I know the time constant is 1? Because I've committed to memory the standard form of the second order transfer function. And the standard form of the second order transfer function has the time constant in this position. So I can look at that and immediately see, time constant is 1. I can actually do a little bit of math and tell you that zeta is 5, just from inspection of that form as well, right? So, okay, so that's super overdamped. What if it's less overdamped? Remember we said a critically damped system would have a middle coefficient of 2, so if the middle coefficient is 1, if I have, in other words, s squared plus s plus 1, at that point those roots become complex, and we now expect to have oscillatory response. If I look at that again, I think of that being zeta is equal to 0.5, which has a pronounced oscillatory effect. Now just putting it out there, you'll see in the textbook we've got a couple of, and when you play with this, a lot of people associate, a lot of people think that if I do this, that will always be oscillatory. But that is wrong. Okay? What it is actually saying is underdamped. And I'll show you now that you only really see a peak in the response around a zeta of about 0.7-ish. So for like a zeta of 0.8, a normal person wouldn't look at that and immediately recognize it as an underdamped response, right? So that the caricature, and this is very, very important, this is where the caricature comes in. I expect you to caricature a second order response this way. Caricature, right? Not because that's exactly the math, but because that gives you a space to talk about things like the overshoot. Now you can tell me through later calculation that upon closer inspection, this system does not exhibit overshoot. But when you caricature an underdamped second-order step response, I expect you to show me some overshoot, because that's the prototypical underdamped response. Is this making sense to everybody? And so if you know nothing more than that, what you can say is that the response is underdamped. You can draw this when you sketch. Okay, remember this is a caricature. This is like you're trying to exaggerate these features. And then if you do later calculations, I may ask you, does this system exhibit overshoot? And you may then go into more calculations. And usually the way that I phrase these questions is I'll allow you to get some easy marks up front without doing calculations, just by like using your intuition, and then I'll dig further into it. And then the smart move obviously is like if you have uncovered some things during calculation, you can go back and just make a note saying, well, note I've drawn an overshoot here, but actually question 2b, in question 2b we notice that we don't actually have an overshoot.